This is Screencast 2, Week 3, 571. And I was talking about basic control charts. Processes in statistical control if its distribution is stable. Ryan, page 26. And for the normal distribution, this means that mu and sigma squared are constant across time. In other words, they don't change value. Now, parameters, you're taught in 210, are fixed values, but you don't know what they are. You don't know what their values are, but you do know that they're fixed. So, here's what we're going to do. We're going to dream up a metric on a business process. We're going to record observations on that metric as time goes by, and we're going to set up a way of detecting if or guessing whether or not the underlying parameter has changed value. If it changes value, we're going to declare that the process is out of control, because after all, it's now not constant. So, how are we going to do this? Well, we're going to use a diagnostic called an X-bar chart to monitor we're going to monitor changes in X bar to detect changes in mu. So here's the classic setup. A metric is a critical dimension of a manufactured part. We're making these parts to the tune of, say, 1 every minute. And we have some sort of an automated measuring system, say with a laser, that measures this critical dimension from every part, which is also called a unit, coming off the manufacturing line. We want to see if the average value of this critical dimension shifts, called a mean shift. So what we're going to do is we're going to, in a with an X-bar chart, we're going to collect a small number of units. We're going to take their average, and we're going to plot this average on a chart that has a horizontal coordinate of subgroup number, and if the X-bar values change a lot, we're going to declare that the manufacturing process, the machinery that's making the part, has gone out of control. Then we are going to shut the line down, called dropping the line, and we're going to look around and try to figure out what has gone wrong. And we're assuming something has gone wrong because our average values have shifted. So when somebody says, well, everything was running, why are you shut the line down? What's wrong? We're going to say, we don't know what's wrong. We're then going to say, well, then why have we shut the line down? We're going to say, our diagnostic tells us that something might be wrong. Well, if you say that to a typical line manager, you're going to say, well, I'm going to march over and I'm going to turn the line back on, because that's nonsense. The only way to have this accepted inside a company is to say, look, this methodology is based on a proven mathematical theorem called the central limit theorem. Therefore, when this chart says, in its opinion, something has gone wrong, we need to take this warning seriously. Otherwise, management's going to say, we're not going to use this system. All it's going to do is cause unnecessary shutting down of our production line for no good reason. So the whole strength of using a control chart is based on the probability theory behind it. So here's the approach. 2 stages. Stage 1 and stage 2. Stage 1 is establish control. And stage 2 is put chart online. Online meaning start monitoring the process in real time. But in stage 1, establish statistical control of sigma squared before establishing statistical control of mu. So it's a little complicated, but this is recommended by Ryan, page 96. So how are we going to establish statistical control of sigma squared when I thought this whole thing was about seeing if this critical dimension was changing, and we were monitoring that with X bar? Well, what you want to do is first create an S chart. Okay, so we're kind of diving into the deep end of the swimming pool as far as quality control is concerned here, because we're getting right down to a real world approach to implementing a quality program. So let's say you're lucky enough to get hired as a quality analyst for a big manufacturing firm. I don't know if you noticed in the news a little while ago, Takata was criticized by some big international manufacturing institute for having no quality control systems in place inside that airbag manufacturing firm. Now remember, Takata has been sued and has been the source of the recall of hundreds of thousands of cars, because their airbags will, when they explode, they send shards of plastic through the face of the people in the car. Turns out Takata was assuming that any problems with their quality would be picked up by the manufacturers who bought their airbags, and that would be done through complaints of the customers who bought those cars. The Institute said, we can't believe this. Here's a company that's making a very high technology item, and they have no internal measures of quality on their product. They're assuming that product liability lawsuits will be their quality control system. You've got to be kidding, basically, is what this institute said. Every responsible high-tech firm now has internal quality control systems in place. Well, what we're talking about here with the X bar chart and the S chart is the oldest and the most used system. And it goes like this. First, create an S chart with data and establish the whether or not sigma squared is in control. Once you've done that, go ahead and create an X bar chart and establish the statistical control of mu. Once those two activities have been completed successfully, put both the S chart and the X bar chart online and start monitoring the process in real time. So you're thinking, well, why don't we just go online first? Answer, Schuhart had a major insight. He said many manufacturing processes are running today, circa 1931-32, that are out of control. It's an embarrassing fact, and it's actually circa 2016, it's true today. There are lots of companies that run out of control processes. So, S chart. We're not going to make that mistake. We're going to first bring the process into control, and then we're going to start monitoring it to see if it steps out of line in the future. What we're going to do is plot S sub I equaling the square root of 1 over n minus 1 sum I equals 1 to n of xi minus x bar squared. So I'm taking the square root of the sample variance, where n is the size of the ith subgroup. I equals 1 to k. K is the number of stage 1 subgroups. So we're going to monitor this guy. Let S equal the average of these K sample standard deviations. An estimate of the process standard deviation is sigma hat equaling S bar divided by C4, where C4 is a tabulated function of n in table E, page 641 in Ryan. So a few more things to get pinned down here. An estimate of the standard deviation of x bar I equals 1 to k is sigma hat x bar equaling sigma hat over the square root of n. Okay, notice when I subscript a a parameter or an estimated parameter, that subscript is telling me what random variable that standard deviation is referring to. If I don't subscript, then that's the underlying variable, the metric that I'm observing. So here I'm making it clear that I'm talking about the standard deviation of my sample means, or my subgroup means. But when I don't subscript, then you can assume that you're looking at this, no bar. And this kind of notation is very common, and it's used in Ryan. But enough of this complexity. Let's start building an example, because otherwise this is all going to seem very obscure. So let's say we have a critical thickness of a plastic part. And we've got a really fancy molding machine which, through great expense, when we mold this part under lots of heat and pressure, we're able to control the thickness, which is no easy task, but in order to make money, we're running at a high rate of speed, and as long as that critical thickness stays put, the plastic part will fit together in the bigger unit, and everything will work. So we decide to start a quality control program on this manufacturing process, and what we're going to do is we're going to use this thickness as our X. So this is our metric. And you could ask the question, well, why this particular thickness? Well, it's been found that this plastic part's thickness has caused many a return unit that doesn't work. You know, something as simple as a snowblower. There's all sorts of plastic parts in there, and if these parts aren't made to the dimensions of the drawings coming out of engineering, the snowblower just won't work. So let's take some stage 1 data. Here's a table. Time, subgroup, values, observations, X bar I, S I, 1, 2, 3, 4, 5, and 6. So here's something that you will get wrong if you don't think about it. Our molding machine can only build one part at a time. Yes, it's cooking away at about one part every 15 seconds. But still, we got this one machine and it does one part at a time, so clearly those parts are coming out of that machine sequentially. Key idea. So if we clump every 2 together into a subgroup, so here we have n equals 2. See, every 2 parts are put into a subgroup, and you can tell that by the subgroup number being the value 1 and 1 for times 1 and 2, and then 2, 2 for times 3 and 4, and so forth. So these time points are every 15 seconds as the machine produces plastic parts. The values on thickness are 2 and 9, 5 and 3, and 7 and 2. Now you're thinking, well, engineering wanted that thickness to be, I don't know, say 4. Well, in the real world, in a manufacturing process, there's no way you can hold such a tight tolerance, i.e., no, no variance at all. Because in the real world, variance is omnipresent. It's ubiquitous. It's everywhere. You can't get away from variance. It's just not going to happen. If you wanted to make parts that had no variance at all, you'd have to spend 10 times as much money on your tooling. And then you might be able to get the variation down to a very small number, but you probably wouldn't get it to go away entirely. There's no way you'd make any money if you spent 10 times more money on your tooling. There would go all your profits. So, statistics handles one critical challenge to making money, and that is, in order to make profits, you have to tolerate variability, because to eliminate variability is expensive. You're not in business to go broke. You're not in business to run at a loss. You're in business to make money. So variability is going to happen, guaranteed. Therefore, you're going to have to figure out some clever way of tolerating variance in your processes. Clever meaning it's there, but you still make money. Control charts are a way to help you manage the presence of variance and still make money. Making money is a lot harder than just running a business. You can run a business at a loss much more easily than you can run a business at a profit. Talk to folks who have tried to make a restaurant go as a profitable business. How many restaurants have gone belly up? Lots of restaurants. So anyway, your means, you can check me out. The average of 2 and 9. 2 and 9 is 5.5 and so forth. And the standard deviations are 4.95 and so forth. You can check these numbers. Be a good idea. X double bar is 1 over k sum I equals 1 to k of x bar I, and in this case it equals 4.666666. S bar, which I've previously defined, is 3.301. So here is a plot of the data. So this is a time series plot, and I'll label it as such. This is X. This is not a control chart. What I'm doing is driving home the idea that these parts are coming out of the machine sequentially. And down here, we have time. And see, we're taking every 2 observations and putting them into a subgroup. So this is a time series plot. Do not draw this plot when you are asked to draw a control chart on a homework question, a project, or an exam, because that's not a control chart. Kind of begs the question, what is a control chart? We will get to that in the next screencast.